Welcome to video 23 in our series on tensor calculus. We've covered a lot of ground in the last 22 videos, and in so doing we've reached something of a milestone. Hopefully today's discussion of tensor equations will help to pull it all together. Let's use this expression to illustrate the properties of a tensor equation. Well, a tensor equation looks very much like a normal algebraic expression. It consists of a number of terms on each side of the equation. Here there's only one term, and on this side we have three terms. Now, each term can consist of one or more factors. Here we've got two factors, here we've got three, and here we have only one. We can also include scalar factors out front, such as this one and this one. Now we can also include the use of things like parentheses if we need to group these terms together. But there are a couple of things that you're not going to see. You're not going to see any fractional expressions, nor are you going to see the use of any exponents. But other than that, the expression does in fact look very much like a normal algebraic expression. Of course, by now you know that we make heavy use of indexes. Free or live indexes are those that appear exactly once in either the upper or lower position of each term. Here I and j are free indexes, and you'll see them in the top portion of each of the terms throughout the expression. Here's I and here's j, and you see I and j here and here. Notice they're not necessarily in the same order. We have I before j here, but j before I there. It doesn't matter. But they all have to be in the upper position, and they have to appear exactly once. Likewise, R and S are free indexes, and you see them here, here, and here. Okay, free indexes, as I say, are used exactly once in each term, and they have to be unique throughout the entire expression. They cannot be used for any other purpose. On the other hand, dummy indexes are those indexes that appear as pairs in each term. For example, K is a dummy index here, M is a dummy index here, as is T, and then in the third term we have both M and K as dummy indexes. So each dummy index appears exactly once in the upper position and once in the lower position of any given term, and they must be unique within the context of that term. They cannot duplicate any indexes that are used in that particular term, either dummy indexes or free indexes. However, the uniqueness is limited only to the individual terms. For example, we've used M as a dummy index here and also in this term. That's completely all right. The fact that we've used M both here and here is completely irrelevant, has no meaning whatsoever. We could have chosen a different letter for M in either position, or we can use the same letter, doesn't matter, as long as there's no duplication within the context of each individual term. Now, an expression structured like this is what we call a variant. Think of a variant as a template or a model. To use it, we simply choose a particular coordinate system to work with and then substitute the specific values for that coordinate system into each of the terms of the expression. Now, all tensors are variants, but not all variants are tensors. So before we know that we're dealing with a tensor equation, we have to know this. We have to know that each side of the equation is in fact a tensor. And for that, I'll refer you back to video number 19, where we defined what a tensor actually is and how to prove if an expression is indeed a tensor. Now, as a practical matter, this is generally not a big deal. For example, if we know that A here is a tensor, then we know that the right-hand side of the equation has to be a tensor as well because they're equal. Also, most expressions that are somewhat complex like this one are built up from simpler expressions that we knew were tensors to begin with. For example, if we know that B is a tensor and C is a tensor, then we know that the product has to be a tensor. So if all of these factors are tensors, then as we multiply them together and add them together, then we know that it makes up a tensor. because we know that tensor products form tensors and adding tensors together form tensors. So usually it's very clean and simple and obvious that one side or the other is a tensor, and if we can prove one side's a tensor, then so is the other. So generally it's very obvious as we work with these things that they are tensors. I will remind you, however, in the discussion in video number 20, that it is possible to take two terms that are not tensors, add them together, and produce a tensor. So the sum of two terms may be a tensor even though the individual terms are not tensors. But as I say, generally it's very obvious and easy to prove that each side of the expression is a tensor. Now I hope you can appreciate what we have here. What we've got is a fourth rank expression, and we know that because there are four free indexes. For example, A here is a fourth rank tensor with indexes I, J, R, and S. Now, you also know that although we're dealing with just one expression, we're really dealing with multiple relationships at the same time. For each value of I from 1 to 3, there can be 3 values of J, 3 values of R, and 3 values of S. Well, that means that there are a total of 3 to the fourth power, or 81 different relationships that are expressed by this one expression. Well, that's bad enough in itself, but if you look at the dummy indexes, if we expand out this dummy index of k, we're going to have a total of 3 terms instead of just one. And because we have two dummy indexes here, that's 3 squared, or 9 terms when you expand this one out, and the same here. So what looks like just a single expression really represents 81 relationships with one term on the left and 21 terms on the right. Now I'll leave it up to you to imagine what it might be like to work with the information in that form, with 81 different equations with one term on the left in each case and 21 terms on the right. Okay, so we have a tensor equation. So what? What's the big deal? Why do we care? Well, the importance has to do with the way these things transform. So let's take a look at that. Let's transform our tensor equation to the prime coordinate system. Now to do that, we substitute the transformation relationship for each term in the expression. For example, this expression is the equivalent of this one. This is what we'd use to transform from the prime system to the unprimed system. We'd multiply by these 4 Jacobian factors. And I'll remind you that that works because we've matched this index with this one, this with this one, these two match with these two, and then the 4 remaining indexes are the free indexes that match up right up here. So these two expressions are the exact equivalent of each other. Well, we do the same thing for each term. This is the equivalent of this one, this is the equivalent of this one, and this is the equivalent of this one. Now, I'll remind you that when we transform a tensor product like this, we need Jacobian factors only for the free indexes. Remember that we ignore the dummy indexes when we're doing a transformation like this. So we don't need a Jacobian factor for k prime here. Well, because the free indexes are the same in each of these 4 terms, then we need the same 4 Jacobian factors in every case. And because that is so, we can now divide all 4 of these factors out, and what we're left with is this expression, and you'll notice that it has exactly the same form as this one. So what we're saying is that transforming from one coordinate system to the other in tensor calculus yields exactly the same formula in any other coordinate system. Now you may remember back in video 1 that the purpose we stated for tensor calculus, the goal, was to create expressions that were independent of the coordinate system that we wanted to work in. Well, a tensor equation is exactly the tool we need. It's the holy grail, it's the golden chalice that we've been looking for. What we can see from this is that if we can express a relationship as a tensor equation, we know that it automatically works in every coordinate system in the same form and in the same way. So, Everything we're doing from this point forward is going to be in terms of tensor equations, because we know when we get a result in one coordinate system, it'll work in every coordinate system. Well, to build on that idea, what I want to do now is to form a contraction of our tensor equation here. I'm going to contract the I-index with S and the J-index with R. And when we do that, the expression is going to look like this. So R and S have become I and J, and by doing so, we formed a full contraction. There are no free indexes in this expression. Because this is a full contraction, there are now 9 terms on the left-hand side of the equation, but they all add together to give a single scalar value. There are a lot more terms on the right, but there's only one expression now, only one equation. Well, because it gives a scalar value, we could just as easily have written it this way, that all the stuff on the right equates to a single scalar value. Well, because of what happens with tensor transformation, we know that this expression over here is the same for every coordinate system, and that guarantees us that when we apply the specific elements here in whatever coordinate system we choose, we're going to get exactly the same value for this scalar quantity over here, and that makes it a scalar function. Now we call this kind of thing an invariant. An invariant is a geometric object that has nothing to do with the coordinate system. You'll notice that there are no indexes here. This has nothing to do with the coordinate system. Now, the beauty of tensor calculus is that we can come up with expressions like this to evaluate our invariant objects. And because of the way these things transform, that gives us the opportunity to use whatever coordinate system is easiest and most convenient, most appropriate in the context of the problem. Knowing in advance that when we do that, we'll get an answer that is the same regardless of which other coordinate system we might have chosen to use instead. So that's the goal going forward, is to come up with expressions like this for geometric objects in tensor calculus. Now, we spent a lot of time talking about covariant objects and contravariant objects, and the thought may have occurred to you, why do we need both? Why couldn't we just represent our objects as covariant objects and be done with it? Well, the answer is that to form these invariant expressions like this, we need both. We have to combine contravariant objects with covariant objects in order to create these invariant relationships. We have to combine them to get the result we want. Now, you're already familiar with this concept. For example, a vector is a geometric object that has nothing to do with the coordinate system, but as a coordinate system, we can represent it if we combine a contravariant object like this with a covariant object like this. It is the combination of these two together that creates the invariant object. Of course, we can do it the other way as well. But that's what you're going to find, is that anytime we come up with a geometric object like this, it will be because we're able to establish a full contraction of objects combining both covariant and contravariant components in tensor calculus to make that happen. Okay, with all that having been said, what I want to do is to wind the video down by going through a summary of the operations that we can use in regards to tensor equations. Okay, well, the first thing we can do is to reorder the terms. These terms are combined with addition and subtraction, and there's no special significance in their order, so we can move the first to the end or middle to the end and that kind of thing. We can also reorder the factors within any given term. We've got this written as DEF. Well, they're multiplied together. We could move the E term to the beginning and the D term to the end, whatever. Multiplication is commutative. Now, I say this because in linear algebra, multiplying matrix A times matrix B is not the same thing as multiplying matrix B times A. Multiplication of matrices is not commutative. But that's not the case with tensor calculus, because whereas the order of this multiplication tells you how to combine the two matrices. That is controlled in tensor calculus by the combination of the indexes. So the placement of the indexes tells us how to combine them, not the order of the terms themselves. All right, well, in any tensor equation, we're free to rename any free index that we want to, as long as it remains unique. So if we didn't like the value of I here, we could change this to a P, as long as we changed it here, and here, and here, and also as long as P is not used anywhere else in the equation. All right, similarly, we can rename dummy indexes. But this time, the only condition is that as we rename the indexes, we have to maintain uniqueness in each given term. So we can rename M here to P, we can rename M here to K. Well, we can't rename it to K because we're using K already, but we could rename it to say something like T. So as long as we rename it to something that's not already in use in the term, we can rename it anytime we want to. And again, we only have to maintain the uniqueness within each individual term. Now let me point out that as you work with tensor equations, you're going to become familiar with this process of renaming indexes, and you're probably going to become proficient in combining these two things together. We say, for example, that we can't rename J to the index M because M is already in use. But if we rename J to M, we could do that as long as we simultaneously rename M to something like K and M here to something like T. So we can combine these and do multiple renaming operations at the same time, as long as we continue to keep all of the free indexes unique throughout the expression and the dummy indexes unique within each of the given terms. Next, we can add a tensor or a tensor expression to both sides of our equation. But remember, anytime we do that, the free index structure has to be the same and consistent throughout. For example, if we wanted to add a tensor t to both sides of this equation, we'd have to make sure, first of all, that it's a fourth rank tensor and that the index structure is ij and rs. It has to be twice covariant and twice contravariant, with the index structure consistent with our equation. But as long as we know that that's the case and that t is a tensor, then as we add it to both sides, the result will be a tensor on both sides, and the tensor equation relationship is maintained. Next, we can multiply both sides of our equation by the same tensor or tensor expression. Now, when we do this, we have to make sure that we do not create any duplication of indexes. For example, it would be improper to try to multiply our expression, our equation, by VI, because I is already in use as an upper index, and that would create a duplicate in the upper position, something that's not allowed. So before doing this, we just need to choose a different letter, such as P. If we multiply both sides by VP, then we're all right, because that's a new index. Now, of course, we could multiply by VI in the lower position, but by doing that, we're really creating a contraction. So it's okay to duplicate the index if there's one on the top and one on the bottom, but we're changing the nature of the index from a free index to a dummy index, and we're also reducing the rank of the expression when we do that. So if that's what you mean to do, that's perfectly valid. All right, well, what about a case like this? Suppose we had T, K, P times Q, K like this. Would we be able to multiply this expression by our equation over here? Well, no, we can't, because we're already using K as a dummy index here, so we can't use K this way as a dummy index. Of course, we could solve that just by renaming K to some other value, but the other way to solve this is simply to rename these dummy indexes right here. So if we were to rename these to T first, then we could multiply by this expression. So you can see from this there are often multiple ways to solve this problem, but in the end you just have to make sure that there are no duplicate indexes, either free indexes or dummy indexes. Next, given the right conditions, we can cancel common factors. Just remember that although this operation may look like division, it isn't. Even so, the effect is the same. For outer products, all we need to know is that the common factors are not equal to 0. For inner products, we need to know that they are arbitrary. Now this might seem quite restrictive, but these conditions are true more often than not. Most of the time, we can simply cancel out common factors. Next, we can raise and lower free indexes or flip dummy indexes. Of course, you know this means multiplying by the appropriate metric tensors, but given that the terms and factors are all tensors, we can do this by inspection. For example, to lower the I index, we'd simply move I into the lower position in each one of the terms. Here, here, and here. The only caution is that we want to make sure we use the appropriate syntax. For example, lowering the I index in this C factor is trivial. We just move the I index into the first position like this in the lower position. But for A, what we need to do is first of all put a placeholder here with J, and I falls here with a placeholder, and then RS. So just go back and review the syntax rules in video 22 and you won't have any trouble. And finally, we can form a contraction between any upper and lower index. All we do is to rename the lower index to match the appropriate upper index. For example, we could rename S to I throughout the expression, and in doing so would form a contraction. Of course, when we do this, we're changing the nature of these indexes and thus the meaning of the expression. So just be sure this is what you mean to do. The key point here is that the tensor relationship is maintained. This operation will reduce the rank of the expression by 2, but the result will still be a tensor equation. Okay, these then are the operations you have at your disposal when working with tensor equations. We'll see numerous examples of each of these going forward. With a little practice, their use will soon become second nature. What we did in this video was to explore the properties of tensor equations. And by way of summary, I have listed what I think are the most important ones right here. Tensor equations look and operate for the most part like simple algebraic expressions. The real challenge is in keeping the indexes straight. So always remember these two very important principles. First of all, each free index must appear exactly once in the same position in each term. Not necessarily in the same order, but in the same position, upper or lower. Also, the dummy indexes must appear as unique pairs within each expression. They have to be unique only within each term, not the entire expression. Okay, so always pay attention to these very critical rules, because if you're working with the tensor equation and you find you wind up with a duplicate free index or a duplicate dummy index, then you know you've done something wrong and things are not going to turn out properly. So these are the keys to pay attention to. And of course, this last point, to be a tensor equation, each side has to be a tensor. Now, this is not generally an issue because we typically build up these expressions from simpler expressions that we know to be tensors. So as you multiply them and add them together, then we remain confident that the expression is a tensor equation. The other major takeaway is this. When we develop a tensor equation like this, which is a full contraction, it produces what we call an invariant. Invariants are geometric objects that have nothing to do with a coordinate system. Well, such an equation can be used to evaluate the invariant value using whatever coordinate system is most convenient. We know in advance that the invariant will evaluate to the same value no matter what coordinate system we choose to use. Now, developing expressions like this is one of the major goals of tensor calculus, and that's exactly what we're going to do in the next video, where we develop an invariant expression for the dot product.